Hi everyone, this is section 4.7 on inverse trig functions. And we're going to start with the graph of y equals inverse sine of x or arcsine of x. Actually, you might prefer this arcsine notation because it's less confusing. And these two mean the exact same thing. The problem with this notation is that a lot of people think that inverse sine of x means 1 over sine of x, or cosecant of x. Now, 1 over sine of x is cosecant of x, as we saw before, but this here does not mean reciprocal. It means function inverse. That's confusing because we're used to thinking that x to the negative 1 is 1 over x. So when we see something like this, we think reciprocal, that the negative 1 is an exponent. But here, the negative 1 is not an exponent. It's just a superscript that indicates function inverse. So again, the inverse sine of x, or arcsine of x, is not the same as the reciprocal of sine of x, or cosecant of x. These are two completely different functions. They're related to sine of x in different ways. Cosecant of x is the reciprocal, the multiplicative inverse of sine of x. But this here, the inverse sine of x, represents the function inverse of sine of x. That's different. These are two very different functions. In general, f inverse is not the reciprocal of f. That's not typically the case that we have equality. All right. Now, in the beginning, we have y equals sine of x. Let's consider the graph of y equals sine of x, the sine wave. But there's a problem when we try to invert this and get an inverse function, inverse sine of x. The problem is that even though this graph passes the VLT, the vertical line test, so we have a function here, the problem is that it fails the HLT, the horizontal line test, which means that this function is not one-to-one. It's not invertible. It fails the horizontal line test. I can take a horizontal line here that intersects the graph in more than one point. In fact, infinitely many points. So what we need to do is that we need to restrict this sine wave. We need to restrict the domain of sine of x in such a way that we follow two conditions. What should this restricted domain be? It should be an x interval on which the sine graph, first of all, passes the HLT, the horizontal line test. That means we can take an inverse. That's an inverse function. And it has to be as tall as the original graph, meaning that the range is the same as before. Because I could say, hey, the origin, the point 0, 0, if I grab that, that passes the HLT. But that's pretty lazy. We would like something bigger than just a point. We would like something as tall as the original graph that has the same range, but a piece of the graph that will pass the HLT. So we want a piece of this sine wave that's as tall as the original graph. It has the same range, but passes the HLT, the horizontal line test. Now, we all agree across the planet that we start at this point, negative pi over 2, comma negative 1. And then where would we stop? Well, we want to pick up the entire range, so we have to keep going, going, going. We want the entire range, and we're going to stop where? We're going to stop here, at this point here, at pi over 2, comma 1. Because we want to capture the entire range for the sine function from negative 1 to 1. Technically, it's a new function here because we're restricting the domain. For the original sine function, the range was from negative 1 to 1. The domain was all reals, but we're now restricting the domain to this closed interval from negative pi over 2 to pi over 2. We have the same range as before. Now, we don't want to go any further because then we're going to we're going to fail the horizontal line test. So we don't want to go any further than this point. Okay, so we all agree that we're going to grab this red piece of the sine wave. from this point here to this point here. And it goes to the origin, 0, 0. So then, how do we go from this restricted sine function to an inverse sine function? We can invert this because it now passes not just the VLT, but the HLT. So remember a key basic principle. Actually, there are 3 basic principles. The domain of one function becomes the what of its inverse function. The domain of a function, a one-to-one function, like this now, becomes the range of its inverse function. Second, the range of this function becomes the domain of the inverse function. And also, the idea that the point A comma B on the original graph becomes what point on the inverse graph? The point B comma A. The idea being that inputs and outputs switch. So based on this red graph here, how do we invert this red graph to get the blue inverse graph? I'll take a copy of my notes here. And here we go. Again, we switch the domain and the range. Let's look at this grid. The restricted domain for sine of x, we just determined that on Desmos. The restricted domain, the x-coordinates go from negative pi over 2 to pi over 2. The domain for the restricted sine function becomes the range for the new inverse sine function. Likewise, the range for both the original and the restricted sine function, the y-coordinates we pick up, went from negative 1 to positive 1, the y-coordinates. The range for the sine function now becomes the domain for the inverse sine function. The domains and the ranges switch. And these are all closed intervals. So observe, the old domain went from negative pi over 2 to pi over 2. That's the new range, from negative pi over 2 to pi over 2. By the way, pi over 2 is about 1.6. So this graph here, if you're using equal scaling on the x and y axes, the graph here is a bit taller than it is wide, if you're using equal scaling. The range on the old sine function here, this is the restricted sine function, from negative 1 to 1, the range on the sine function now becomes the domain on the inverse sine function. So the y-coordinates here, from negative 1 to 1, now become the x-coordinates here, from negative 1 to 1. That's why I'm putting these tick marks on the x and y axes. Domains and ranges switch. Let's take a look at things point by point. The point 0, 0 lies on the old graph, so the point 0, 0 lies on the inverse graph. The point negative pi over 2, comma negative 1 lies on the old sine graph. By old, I mean the restricted sine graph. The point negative 1, negative pi over 2 lies on the inverse sine graph. Remember, AB goes to BA. We switch the coordinates. Likewise, the point pi over 2, comma 1 becomes the point 1, comma pi over 2. A few other observations. First of all, notice that the restricted sine function is still odd. The inverse of an odd function is odd. That is true. This blue graph, this inverse graph, is also symmetric about the origin. Second, the red graph here is going up. The restricted sine function is increasing, and the inverse of an increasing function is also increasing. This graph is also going up from left to right. For example, remember temperature back in section 1.9. So as things got warmer, both Fahrenheit and Celsius temperatures went up. Fahrenheit and Celsius temperatures went up together, or they went down together. X and Y both went in the same direction. Same thing here. X and Y go in the same direction here. X and Y go in the same direction here. Now, at the endpoints here, the graph goes flat. We have sort of one-sided horizontal tangent lines over here and over here. I'm putting those in green. The horizontal tangent lines here become vertical tangent lines over here. Now bear in mind, these green tangent lines are not actually part of the graph, but I'm using that as a visual aid. These two green tangent lines. The horizontal tangent lines on the old graph become vertical tangent lines over here, meaning that even though the red graph went flat near the endpoints, the blue graph becomes steep near the endpoints. Also, the concavity changes. This graph goes from concave up to concave down. This graph goes from concave down to concave up. But if you remember that the graph gets steep near the endpoints, you don't have to remember that. That's just natural when you graph it. The big picture. Notice here, this red graph has finite length or arc length. This is the entire red graph here. The blue graph here, this is the entire graph of y equals inverse sine or arcsin of x. It has finite arc length. And you can find the length of this in calculus. All right. Now, before we go on, I'd like to show you this in Desmos. Again, here's a graph of y equals sine of x. If you put the line of reflection, y equals x here, notice that x and sine of x are very close near the origin. That's no coincidence in calculus. What if we graph y equals arcsine of x? Well, it might be kind of hard to see, but the piece of the blue graph from this point to this point, if you reflect it about the green line y equals x, you get the purple graph. It's a bit hard to see. By the way, instead of arcsine of x, you could actually do sine with the -1 superscript. It's the same graph. Now, actually, if you care about the coordinates of the inverse sine graph, remember, domains and ranges switch. So notice that here, the domain for the restricted sine function was from -π/2 to π/2. The domain for the restricted sine function now becomes the range for the inverse sine function. Y equals arcsine of x, the arcsine function. The range now goes from -π/2 to π/2. Here's the point -1, -π/2. Here's the point 1, π/2. And likewise, the range here from -1 to 1, the y coordinates, becomes the domain here, the x coordinates, from -1 to 1, from here to here. Domains and ranges switch. Which means, again, these fractions of pi, they're better for the x-axis when you're talking about the original restricted sine function, but they're better for the y-axis when you're talking about the inverse sine function. We'll talk about the inverse cosine and inverse tangent functions, their domains, ranges, and graphs next time.